Welcome once again. In this session, we are going to discuss noise performance in SSB receiver. So first we consider SSB wave, which include only lower single sideband. And it is S function T equals to AC upon 2 mt cos 2 pi fct plus AC by 2 m cap T sin 2 pi fct. Here the first term is called in phase component and the second term is called quadrature component. Here plus sign between two terms represent lower single sideband is retained while upper single sideband is filtered out. This wave is also called amplitude modulated single sideband suppressed carrier wave. And the generation of SSB has already explained in detail. You can also go through that video lectures. Here we consider SSB receiver and then explain noise performance. As we have seen in SSB wave equation, also called as SSB suppressed carrier wave, M cap T is called Hilbert transform of massive signal MT. Here Hilbert transform is a type of linear filter denoted by capital H function f, and it is a type of signum function. So HF equals to minus J signum of f function. That is called Hilbert transformer. So for a given input m function t, Hilbert transform becomes m cap function t. Here both massive signal and its Hilbert transform have same average power equals to capital P. So in SSB wave, first term include massive signal mt with cos 2 pi fct and it is called in phase component, and the second term include Hilbert transform m cap t multiplied by sin 2 pi fct known as quadrature component. Here the plus sign between the two terms represent lower sideband is retained. Now on comparison basis, we know that double sideband suppressed carrier wave is given by S function T equals to AC mt cos 2 pi fct, and the average power of this double sideband suppressed carrier become AC square upon 2 into P, where P is called average message power. Therefore, we can say that average power in single sideband suppressed carrier is just half of the double sideband suppressed carrier. So, for SSB, average power become AC square upon 4 into P. Now, as SSB contains in phase and quadrature component with the same average power, and since total average power of SSB is AC square upon 4 into P, so we can say that the average power of both in phase and quadrature component is half, and it is AC square upon 8 into P. Next, for noise performance, we first derive input SNR or called pre-detection SNR. In SSB suppressed carrier, the transmission bandwidth is equals to W, which is same as message bandwidth. And the average signal power for SSB is given by expectation of S square T, and it is equals to AC square upon 4 into P. Also the average noise power given by expectation of N square T equals to N naught into W, where N naught is called average noise power per unit bandwidth, and here the bandwidth is W. From here we can write input signal to noise ratio equals to AC square P upon 4 N naught into W. Next, for post-detection SNR, we consider a receiver model which contain bandpass filter, product modulator including local oscillator and then low-pass filter. Input is received SSB wave denoted by S function T, and while transmission through a channel there is an introduction of additive white Gaussian noise denoted by W function T. So the input is ST plus WT. After passing through bandpass filter, we get filtered signal denoted by X, and it is equals to S function T plus NT. Here N is called narrowband noise, also called as filtered noise. The purpose of the bandpass filter is to convert front end receiver noise WT into narrowband noise NT and become compatible with received SSB signal having same bandwidth of W. After this, product modulator and low pass filter is used for detection purpose. Here the output of the product modulator V function T is simply the product of input signal xt and locally generated sinusoidal carrier cos 2 pi fct. And at last, product modulator output is passed through low pass filter and higher frequency component get cancelled and we get output which is corresponding to the low frequency message signal. Now for the derivation of output SNR, we use output of the product modulator, that is V function T equals to xt cos 2 pi fct. Here x equals to s plus n. Here s is called SSB, suppressed carrier wave, and n is called narrowband noise. Here the SSB wave having in phase and quadrature component, and it is equals to AC upon 2 mt cos 2 pi fct plus AC upon 2 m cap t sin 2 pi fct. Also narrowband noise having in phase and quadrature component, so it is equals to ni cos 2 pi fct minus nq sin 2 pi fct. Here we note a point in case of SSB, plus sign is in between two terms, which means lower SSB is retained only. After opening the bracket, we get four terms. In first and third term, we use formula cos square equals to 1 plus cos 2a upon 2, and here a is 2 pi fct, and in second and fourth term we can put sin a cos a equals to sin 2a upon 2. So after this arrangement we get b function t equals to 1 upon 2 within bracket ac upon 2 mt plus ac upon 2 mt cos 4 pi fct plus 1 upon 2 within bracket AC upon 2 m cap t sin 4 pi fct plus 1 upon 2 within bracket ni plus ni cos 4 pi fct minus 1 upon 2 within bracket nq into sin 4 pi fct. Now combine cos term and sin term together as well as remaining terms and we get v function t equals to 1 upon 2 within bracket AC upon 2 mt plus ni plus high frequency term. So these high frequency terms that is centered at twice of Fc can be removed using low pass filter. And output of low pass filter become y equals to 1 upon 2 within bracket AC upon 2 mt plus ni. And here we see output y is free from quadrature noise component as it is completely removed by low pass filter. And output y is combination of scaled message signal plus in phase noise component. And from output we can find output SNR. Since at the output signal is AC upon 4 into mt and its average power is given by expectation of s square t and it is AC square upon 16 into p. Also at output noise term is half of in phase component. And in order to find average noise power at the output, we consider power spectral density of narrowband noise as shown in figure. In case of single sideband, transmission bandwidth is W. Therefore, the average noise power is N0 into W, where N0 is called average noise power per unit bandwidth. Also in SSB, the in phase and quadrature component contains same average power, so we can say that average noise power in phase and quadrature component is N0 W upon 2. Using this, in case of single sideband, output contain half of the in phase component. So the average noise power at SSB output is expectation of n square t equals to half of N0 by 2 into W and it is equals to N0 upon 4 into W. Therefore output SNR equals to average signal power upon average noise power and it is equals to AC square P upon 4 N0 into W. Next, for the analysis of noise performance in SSB receiver, we can use reference model of transmission, that is a type of baseband transmission. Here the reference input signal is SSB suppressed carrier wave whose average signal power is AC square upon 4 into P, where P is called average message power. In SSB, transmission bandwidth is W, so average noise power is N0 into W, and therefore the reference signal to noise ratio become AC square P upon 4 N0 into W. After this, we can find figure of merit, and it is equals to output SNR upon reference SNR. Output SNR has already calculated, which is same as reference SNR, so we can say figure of merit is unity and it is same as double sideband suppressed carrier. From this discussion, it is concluded that noise performance is identical for single sideband suppressed carrier and double sideband suppressed carrier. Also, noise performance of vestigial sideband using coherent detection is similar to that of single sideband suppressed carrier.